Hi everyone. In this video, we will explore the definition of the Riemann integral. To begin, I want us to recall from the previous video the definition of the upper and lower Darboux sums. So, to define the Darboux sum, we defined on each subinterval of the partition a value capital M sub k, which was simply the supremum of the function over that subinterval, and a value little m sub k, which was the infimum of the function over that subinterval. We then define the upper and lower Darboux sums of f relative to the partition P as the upper sum being the sum of the areas of the rectangles where you take the supremum value as the height of your rectangle times the length of that subinterval, multiply those together to get the area of the rectangle, and add them up. Similarly, for a lower sum, we used the value little m sub k, so we use the infimum of the function over that subinterval times the length of that subinterval, multiply those together to get the area of the rectangle, and then added up each of those areas to get the lower Darboux sum. These are both going to be very important as we begin to develop our formal definition of the Riemann integral. And in fact, before we even get that far, we want to first look at a few facts about upper and lower Darboux sums, which will be important to our study moving forward. So a couple of quick facts. So the first fact I want us to observe is that if we sort of think about the three different kinds of sums we looked at in the previous video, lower Darboux sums, upper Darboux sums, and Riemann sums, for any fixed partition P, the lower Darboux sum must be less than or equal to the Riemann sum, which must be less than or equal to the upper Darboux sum. Now, why is this? Well, this follows from the simple fact that on each subinterval, f of any tag value on that subinterval, let me actually use k as my indexing variable. So f of c sub k must be less than or equal to capital M sub k and greater than or equal to little sub m sub k, right? So this is the infimum of the function over the kth subinterval. This is the supremum of the function over the kth subinterval. And any particular value of the function must be between these two values. So using that fact, it's then easy to take each of these. We'll multiply by the positive value delta x sub k. So again, that's going to preserve our inequality. And so what this gives us essentially is that each of the areas of the rectangles formed on that kth subinterval will be ordered in this way. And now we can simply sum, since this is true for each k, then it must follow that the sum over k must also be ordered in this way. And of course, these things are then precisely the lower Darboux sum, the Riemann sum, and the upper Darboux sum. So we get this nice ordering. Visually, right, you can think of this as simply, if I were to just sort of sketch a picture here, right? So I have my function, and just imagine I'm looking on, the kth subinterval. And suppose my function looks like this. If I have a particular tag value sitting somewhere here, then the Riemann sum would be represented by this rectangle. The upper Darboux sum would be represented by the largest value over this subinterval is occurring at the right-hand endpoint. And the lower Darboux sum looks like the minimum value for this function occurs about here. the lower Darboux sum would be sitting here, right? So again, lower Darboux sum less than or equal to the Riemann sum less than or equal to the upper Darboux sum. So you get this nice ordering of these upper and lower Darboux sums and Riemann sums. Now, the second fact is a little more subtle. So suppose we have two partitions. I'm going to call them P1 and P2. And what I've written here, I've written P1 is a subset of P2. So how should we think about this? We should really think about these. These are both partitions. And the partition P2 contains all of the points of P1 plus some other points, okay? So we would often say that maybe P2 is a refinement of P1. It contains all the points of P1 plus some other points, okay? So we would say here that P2 is a refinement of P1. So we have these two partitions. P2 is a refinement of P1. If that is the case, then the lower Darboux integral of P1 of f, or P1f, must be less than or equal to the lower Darboux sum P2f. And for the upper Darboux sums, the upper Darboux sum of P1f must be greater than or equal to the upper Darboux sum of P2f. Now, this can seem a little strange at first, and let's just sort of sketch a picture here to help us understand why this is true. So imagine in the simplest case, I have some interval AB. The easiest partition I can have of an interval is just take the two endpoints, right? The 2-point partition. Okay. So imagine I have a function here, okay, sitting somewhere on here. Okay. If I were here to take my upper and lower Darboux sums, as I've drawn it here, my lower Darboux sum looks like would just be using the left endpoint. So this represents like L, P1, F. And my upper Darboux sum looks like might occur right about here. So in orange here, like this would be my upper Darboux sum of P1F. Okay. Now, what if I came in here and I threw in another point of my partition? So I came here and maybe I added in a point x1 into my partition. Okay. Now let's think about my upper and lower Darboux sums. So if I were to come in here and draw a lower Darboux sum for P2, okay, so what would I do? First, I would look on this interval a to x1, find the smallest value. That's still actually going to be at the left endpoint. And I would draw this in here. And then on this subinterval, I would find the smallest value of my function. That would be here. Okay. And so I would end up with my lower Darboux sum being this area in red here. Notice that that area is larger than the area in green, which was the lower Darboux sum for P1F. So in red here, you have the lower Darboux sum of P2F, which we can see, having added in an extra point into my partition, that lower Darboux sum on the refinement is actually larger. So that's what this sort of first piece is saying here. If you have more points, if you add more points into your partition, you're going to make the lower sum larger. And notice sort of why that is. It's really fundamentally comes down to the fact that if I take the minimum value of this function, or the infimum of this function, over the big set AB, then that value is going to be less than or equal to the infimum over any subset. Okay, so when I break this up, now on this subset, I actually have the same infimum that I had on the larger set. But on this subset, my infimum has actually gotten larger. Okay, And so therefore, I'm actually getting a slightly higher rectangle here than I had on the whole set before. Okay. Now, the same thing happens essentially, but in reverse for upper sums. So if I come over here for my upper sum, right? If I look on this subinterval, I'm going to get the same rectangle because on this subinterval, I have the same maximum value. However, on this subinterval, my largest value is here. Okay. And so when I compare these two rectangles to the large orange rectangle, right? These two rectangles have less area than the large orange rectangle. So the upper sum of P1F here is actually greater than or equal to the upper sum of P2F represented here. Okay. So again, you get this ordering of upper and lower sums as you take refinements of partitions, so as you add more points into your partition. Now, with this in mind, we now want to look at defining what we're going to first call an upper and lower Riemann integral. Okay, so suppose f is a bounded function, and then we will define the upper and lower Riemann integrals to be, so the upper Riemann integral, which we'll write as sort of this integral from a to b with a line over the top. So the upper integral of f is equal to the infimum over the set of all partitions of the upper sums of those partitions. Sorry, the upper sums of f over those partitions. So the idea here is define the upper Riemann integral to be the infimum of all of the possible upper sums of that function. So take that function, take every possible partition, and take the upper sums of that function over the partition, the upper Darboux sums, then look for the infimum of all of those. So look for the greatest lower bound. Okay. Similarly, we will define a lower Riemann integral. The lower Riemann integral of f will be take all the possible partitions of AB, look at the lower Darboux sums of f over that partition, and take the supremum of all of those. Okay. Now we'll look at a few pictures in a bit to help us sort of visually understand what this represents. But just formally, we're going to define the upper Darboux sum to be the infimum of all of the upper sums, and the lower Darboux integral, or sorry, the lower Riemann integral, sorry, upper Riemann integral, lower Riemann integral, the lower Riemann integral to be the supremum of all the lower Darboux sums. Now, the first question you might ask is, well, like, that's a fine definition, but do these things even exist? So it actually turns out that for a bounded function, these values are always guaranteed to exist. Let's think about why that is true. Let's think about this set of upper sums. So we'll do this for an upper Darboux integral. So you can sort of imagine here, if I were to break this out a bit, really one way to think about this is I'm taking the infimum of the set of all upper sums of f such that P is a partition of AB. So how do I know that this infimum exists? Well, if I knew that this was a non-empty bounded set of real numbers, then I would know that the infimum has to exist. Okay. And in fact, I really just need bounded below here. Okay. How do I know that this set is bounded below? Well, in particular, one of the nice facts about these sums is that UPF for any partition, right, is greater than or equal to that lower sum. That's using that first fact of um, of Darboux sums that we just looked at on the previous slide. Okay, so I know that for any partition P, this is the upper sum is bounded below by the lower sum, and the lower sum, right, using that refinement property, the lower sum of any partition F will be bounded below by the partition that just consists of the 2 points AB of F. That's using that refinement property. This is the smallest possible partition of AB. Every other partition of AB can be thought of as a refinement of this partition. And so whatever this value is, right, this has to exist, right? This value, in fact, is just the infimum of F, right? The infimum of F of X over the interval AB times B minus A, the length of the interval, okay? The infimum of this function, because it's a bounded function, must exist. So whatever this value is, I know all of my upper sums for any partition are bounded below by this. So this is a non-empty bounded set of real numbers. It's actually bounded above also. It's bounded above by the upper sum of the trivial partition. So this is a non-empty bounded set of real numbers. Its infimum must exist. Okay, a very similar argument can be made for the lower sums, right? And so therefore this supremum must exist. So the upper and lower Riemann integrals must always exist for a bounded function. Now, of course, if you remove the condition that it's bounded, you run into some difficulties. If your function f is not bounded, then you don't know that these infimums and supremums necessarily exist and are finite, so you can have some problems. But for a bounded function, these upper and lower Riemann integrals are always guaranteed to exist. So that brings us then to our definition of Riemann integrability. Simply said, we say a function is Riemann integrable if the upper and lower Riemann integrals themselves are equal. So a bounded function on the interval AB is Riemann integrable if and only if the lower Riemann integral is equal to the upper Riemann integral. And if that's the case, then we write the Riemann integral of f is equal to that common value of the upper and lower Riemann integrals. Yeah. All right. We'll do a couple examples of this, but before we do this, let's sort of look through and think about an example. So, or just visually. So you can imagine you have some function f on the interval AB. Here's an example where you can sort of see here the darker shading here is, or I guess this is maybe sort of the lighter pink purple shading here, is actually just representing our lower Darboux sum. And then we have an upper Darboux sum. This is a partition with 4 points. Okay, so it's a fairly coarse partition. What if we took a refinement of that partition? Okay, so what if we added some more points into our partition? So you'll see here, right, the first thing to notice is going from here to here. Notice that the lower sum, so these sort of pink-purple rectangles, their total area goes up, right, because I've taken a refinement of that partition. The upper sum has gone down, right? Okay. But notice also that their values are getting closer and closer together. You can sort of realize these areas in between, right, as the difference between the upper and lower Darboux sum. So that's gotten smaller. And again, if I take another refinement, again, those values are getting closer together. Another refinement, those values are getting closer together. And the idea is, right, eventually, if I take the supremum of all the lower sums, that gives me my lower Riemann integral. If I take the infimum of all the upper sums. That gives me my upper Riemann integral. And if those values are the same, then we will say my function is Riemann integrable. And what I'm really recovering is the area of this region. Okay. All right, so let's look at a couple of specific examples and work through some of the details related to actually using this definition. All right, so imagine, let's start by trying to find the integral from 0 to 1 of the function x cubed. So the first thing to recognize, this is a bounded function, so it does in fact make sense to talk about the Riemann integral under our definition. And so let's first try to think about what an upper and lower Darboux sum might look like. Okay. Now, in general, this would be difficult because we don't like, what partition should I look over, right? That definition says look at the infimum over all partitions. So we're going to start by looking at a particular partition, at a sort of uniformly spaced partition. So we're going to start by choosing a partition, and it's going to be a family of partitions, P sub n, which are going to be the partitions of the form 0, 1 over n, 2 over n, so on and so on and so on, all the way up until we get to 1. So this is just, P sub n is just the partition of 0, 1 with n plus 1 points, right? So you've just broken them up into, this is a uniformly spaced partition. Each subinterval has width 1 over n, okay? So let's think about what are our upper and lower Darboux sums going to look like? Now, by definition, and I'm going to not always carry the indexes on these sums. This is from k equals 1 to n, but to save a little bit of writing, I'm just going to drop them for the time being. Now, if I think about this maximum value here, let me first think about the fact that this function x cubed is monotone increasing on the interval 0, 1. Okay. So what that means is the maximum value of the function is going to occur at the right-hand endpoint of any subinterval, right? My function is always increasing, so the maximum is going to occur at a right-hand endpoint. So when I look at something like this, I think, okay, the maximum of the function is going to occur at the right-hand endpoint. So the maximum is going to occur at x sub k, but my function is x cubed. So the maximum value of the function is going to be x sub k cubed, and then I'll have times delta xk. Similarly, the minimum value of this function x cubed is going to occur at the left-hand endpoint of my subinterval. So it will occur at x sub k minus 1, but then the function is x cubed, so the minimum value will be x sub k minus 1 cubed times delta xk. Now, plugging in what those values are, so the right-hand endpoint of the kth interval will just be k over n, and the width of every subinterval, but in particular the kth one, is 1 over n. Down here, the left endpoint will be k minus 1 over n. And again, the kth subinterval has width 1 over n. And now if I do a little bit of algebra here, I'll get a k cubed over n to the 4th. And here I will get a k minus 1 cubed over n to the 4th. And now this is where I want to just bring back the fact these are sums k equals 1 up to n, k equals 1 up to n. The sum is indexed over k, which means that anything that isn't to do with k is a constant as far as the sum is concerned. So I can pull out, for example, a factor of 1 over n to the fourth, and I'll be left with the sum of k cubed, k equals 1 to n. And similarly here, oh, now this is where it'd be really nice to have some expression for this sum in terms of n. And we can actually get such a sum. I'm going to sort of slightly sidestep the issue of how we calculate the sum because it's not exactly the point of this course. But there are ways of calculating. This is the sum of the first n perfect cubes, right? So this is really 1 plus 8 plus 27, so on and so on and so on, all the way until you get to n cubed. This is actually very similar because it's just shifted down by 1. So this would be 0 plus 1 plus 8 plus 27, so on and so on and so on. Okay. But we can come up for an expression for each of these and then multiply by 1 over n to the fourth. I want to sort of skip to the punchline again, to sort of emphasize what I think are actually the important things. From here, using a formula for the sum of the first k cubes, we actually get that this upper sum is 1/4 n plus 1 squared over n squared. And we get that the lower sum of p sub n f is equal to 1/4 n minus 1 squared over n squared. Okay. Now, what can we observe about these? Well, first, notice that as n goes to infinity, so as I take more and more points in this partition, this will go to 1/4 as n goes to infinity. So right in particular, this term will go to 1 as n goes to infinity times that. And similarly here, this term will go to 1 as n goes to infinity. So I'll be left with 1/4 as n goes to infinity. Okay. Now, notice that this doesn't necessarily mean, at least immediately, this is just saying for this particular type of partition, as I take more and more points in my partition, the upper and lower sums of those tend towards 1/4. But I can use this actually to help me see that, in fact, any partition as I take the infimum over all partitions of the upper sums and the supremum over all partitions of the lower sums, I will actually get 1/4 for both of those. Okay, so let's see how we can use that to our these facts here to our advantage then. So we want to sort of use the fact that if I look at the lower sum of P sub n f, then for any arbitrary partition Q, this is a refinement of P sub n. I'm adding in a bunch of other points Q, okay? So we would call this the common refinement of Pn and Q. So for an arbitrary partition Q, right, I would get this. This, of course, is less than or equal to the upper sum over this same partition, which is less than or equal to the upper sum of just Pn of F. Okay. So the idea here really is that if you had any other partition Q, right, both of these are going to 1/4, right, as n goes to infinity. For any other partition Q, right, if you look at its common refinement with P sub n, then that Q, right, the common refinement of P, n, and Q, these must also be going to 1/4. They're being squeezed to 1/4. And so for any arbitrary partition, as you take the infimum over arbitrary partitions, that infimum of the upper sums is being squeezed to 1/4, and the supremum of the lower sums is also being squeezed to 1/4. And so, right, we end up with the result that we want, which is, of course, that the lower Darboux sum of x cubed is equal to 1/4. So this is coming from the infimum of the upper sums. We also end up with the upper sum, or sorry, the upper Riemann integral of x cubed is also 1/4. And therefore, since these are both equal to each other, then we have that our function is Riemann integrable, and so the value of the Riemann integral is precisely this. Okay. Now, notice there's a lot of both technical and theoretical work that goes in here. I mean, first we need to calculate the sums over these uniform partitions. That requires, being able to calculate some particular sum of cubes. We do that, and then we still have to try to explain why, this will still work for arbitrary partitions. So there's a lot of work that goes in just to finding the integral of x cubed, right? We probably don't want to do this by hand all that much, right? So what we're going to want to do is develop some theory that will take a lot of this technical work out of things, right? And so in the next video, we'll start exploring that alternate sort of characterizations of Riemann integrable functions. But before we do that, I do want to look at one more example, and we're going to go back to this characteristic function of the rationals, which we looked at in the previous video. So if you will recall, in the previous video, one of the things we mentioned is that if you look here at the upper Darboux sum of, let me actually write what this function is. If you look at the upper Darboux sums of this function, you actually always end up on the interval 0, 1 with 1. And if you look at the lower Darboux sums for any partition, you always get 0. So this is true for any partition. So using this, if we then look at, right, what is the upper Darboux integral? Okay. Well, the upper Darboux integral of this function right, by definition, it's the infimum over all partitions of the upper, but each of these is 1, right? All of them are 1. And so the value of this upper Riemann integral just turns out to be 1. The lower Riemann integral, if I think about what that is, this is the supremum over all partitions P of the lower Darboux sums. But each of these, for every partition, that's 0. So you're taking the supremum of a set which consists only of the value 0, that is 0. And in this case, these are not equal to one another. Okay? And therefore, this function is not Riemann integrable. So this does not exist. Now, I do want to show you here and just quickly point out something. One of the dangers of only ever working with sort of right-hand rule, left-hand rule. Okay. So in this particular case, if we were to think about this as just a right-hand rule, like sort of a problem like we might have done in calculus, right? We might be tempted to do the following, right? We might be tempted to say, well, okay, let's just calculate a right-handed Riemann sum. Now notice, I want to point out here, I'm not talking about Darboux sums now. I'm imagining we're back in calculus and we're just thinking about a right-hand rule Riemann sum on a uniformly spaced partition. So if I was to take, a Riemann sum that looks like, f of k over n times 1 over n for k equals 1 to n. I'm thinking of my function f as being this function here, right? So this would be some k equals 1 to n of I sub q of 1 over n times 1 over n, or of k over n, sorry. But if I look at these, each of these is rational, right? So this function would just return 1. Okay. So I would just get a sum of n, right? 1 to n, values 1 over n. This would just be n over n, which is 1. Okay. And what this would say is that the Riemann sum is always 1. For this right-hand rule, the Riemann sum is always 1. And so in a calculus class, often you just said, well, take more and more rectangles, right? So I would define this. This would be the limit as n goes to infinity of the constant 1, which is just 1. So in this case, sort of using the notion from calculus, you might think that this is Riemann integrable and has Riemann integral of 1. So what's going wrong here? Well, if you read your calculus book very carefully, it's likely that when they started discussing integration, somewhere at the very beginning, the first time before they even defined Riemann sums, they said something to the effect of, let's just assume all of our functions are either Riemann integrable or continuous. Okay. If you know that your function is Riemann integrable, then you can actually use any partition you want and just take refinements of that so that the norm goes to 0, and it is guaranteed to converge to the value of the Riemann integrable, of the Riemann integral. Because by assuming that it's Riemann integrable, we already know that that value is going to exist. So we know that the upper and lower Riemann integrals are going to be the same. And so you can take sort of any subsequence you want of partitions, as long as the norm of the partitions is going to 0, and those will converge to the value of the Riemann integral. What's happening here, though, is that this is not Riemann integrable. And what we have just shown when we showed it was equal to 1, we show that there's some sequence of partitions whose norm is going to 0 so that this converges to 1. But you could have easily picked another partition, another tagged partition, right, and shown that they were 0. So the problem here is that the standing assumption that your calculus book made, which was that every function you're going to be working with is Riemann integrable, is no longer true here. Now, I've also mentioned that your calculus book may have said, let's just assume all functions are continuous. We will actually see in the next video that all continuous functions are Riemann integrable. So again, by making an assumption that your function was continuous, they were also assuming that your function was Riemann integrable, and therefore you could use an easier to work with definition of the value of the Riemann integral. However, this is an analysis course at the graduate level. We're not going to make those sorts of standing assumptions. So we do have to be more careful, as we've seen in this video, with determining whether functions are Riemann integrable or not. That concludes this video. In the next video, we will look at some alternate characterizations of Riemann integrability. So as I mentioned, we will look at the proof that all continuous functions are Riemann integrable, and also that all monotone functions are Riemann integrable. In addition to coming up with some equivalent definitions of Riemann integrability, which will be helpful to use in certain situations.